He and I have been observing for less than 40 years.
Dan, when did you move to Spokane? Was it 82?
Forgot I was muted. Yeah, it's been 38 years.
That's how long I've known him. You see that northern lights behind him? When we saw those, we'd pack up and go home. Oh, crap. We can't observe tonight.
That's
Mikey.
Anything else you need?
How's New York? Mike, can you hear us? This is a mic check.
Happy birthday.
Happy birthday, Neil.
Birthday, Neil.
Thank you kindly. You're a couple of days early.
Well, better early than late.
Yeah,
Just want to let you know we're thinking about you.
So Mike, since you're now connected, you could lead the meeting now, right?
No,
How's New York going?
I'm sorry.
How is New York going?
Oh, it's fine. We're in Little Italy and I'm so sick of food. It's unbelievable, but it sure is fun. You can't believe how crowded it is. It's like ants everywhere, reminding me of China, but it's really cool. It's really neat.
Well, ladies and gentlemen, we're going to get this road on the show. So I'm going to call the meeting to order, the September meeting of the Stockton Astronomical Society. I'm Jeff Baldwin. I'm the vice president. And I'm going to be running the meeting tonight because Mike is in New York instead of right here where he's supposed to be. So before we kick in with our guest speaker, I do want to say that this is our second. I either had us. Are we good? Okay, we're experimenting with the lights, I guess. I do look better in the dark, don't I? So nodding too. So this is our second live meeting since the great COVID-19 pause. And we have, I think it was 8 at my last count. So present here, myself, Jeff Baldwin, Larry Grimes, Paul Kostick, Chrissy Abbott, Jerry Hyatt, Bill Lytell, Doug Christensen, Eric Holland. Did I miss anybody? So that's like 8 people finally at a live meeting, which is, it's 8, but we'll build this up some more later. Because as time goes, we're going to want to kind of get back into the swing of things. Everybody who showed up tonight, thank you for coming, and people on Zoom, thank you. So I'm going to go directly to our guest speaker tonight, Dan Bakken. we were just talking, I've known him for 38 years. Back in, I guess it would have been 84 then. He came over to the Spokane Astronomical Society from the Seattle area, and he and I and Tim Rodriguez and Grant McKinney were the 4 horsemen of the apocalypse. We were absolutely the most troublemaking morons on earth, but we were the most serious observers in the club. And for example, when we go to the Table Mountain Star Party in Central Washington every year, there'd be 200 or 300 people there, eventually up to like 600 or 700. And at 4 o'clock in the morning, we'd be the only 4 still observing. And we've been like that for 4 decades now. Dan got a degree in physics at Eastern Washington University and was, I guess the term would be a crystal engineer. And he had his own crystal company, and I believe he sold it. And not sure what you're doing now, Dan. He has been a deep sky observer. He and I did our Herschels, and then we both did our Herschel 2s, and of course, our Messiers. And for those of you who know, that is an extraordinarily challenging project to take on and to complete. He has built a magnificent telescope for, at some point in time, it was the largest amateur telescope in America, if not the world, a 41-inch f3.9 named Hercules. And it was originally a Kriege-style Dobsonian. He has converted it to, I guess the term would be a flex scope, and he could talk about more about that later. So you can see in that picture on the screen, you have to climb a very tall ladder in the dark to look through it, which is why I make F3 telescopes. It is the king of all star parties everywhere it goes. And Dan has given presentations before on the human eye and deep sky observing and how they work together. And it's very interesting. And I'm hoping that that is the direction that he's going to be talking on tonight. So I'm going to stop talking and I'm going to hand this over to Dan Bakken.
All right, thank you, Jeff. Jeff and I have known each other for 38 years. I just did the calculation here in my head. And it's been a great time knowing Jeff, and he's a great, good friend of mine. And thank you so much for inviting me tonight. And I've given this talk a few times over the years for different astronomy clubs. And so hopefully it'll strike the right balance between beginners and some people that have been doing this for years. Hopefully all of you will get something out of this talk here. So as you can see here, this is actually doing what I'm talking about tonight. And that is looking at the stars through a telescope typically. And even naked eye observing can count here for many things. But let's start moving in here into the, just a second. Okay, there we go. So the first thing I want to say is deep sky observing is not easy. A lot of people think you just look in a telescope and there you go. But it's a lot more than that if you want to get as much as you can out of it. I mean, certainly you can do whatever you want, but I would suggest trying to take a few notes and think about what you're doing when you're doing it to get, again, the most out of it. And so let's take a look here. So when newcomers are first introduced to deep sky observing, they're usually let down by the lack of brightness and color. You know, I think a lot of people are expecting to watch some kind of a Star Wars sequel when they look in a telescope, but that's not exactly what it is. So things are usually a lot more subdued, but they can be very sublime in their own way. And so even today, there's so many awesome photographs, astro images, I guess you technically call them. Photographs are chemical processes, which we don't really use much anymore. But anyway, these images can be fantastic. And I'm not trying to take anything away from looking at those images or participating in the wonder and awe of looking at that stuff in that way. But there is something very special about actually putting your eye behind an eyepiece and looking at this stuff for real, to actually sense the actual photons coming from these things can be millions and millions of light years away. And so to me, there's nothing that replaces that. There's a very subtle but very tangible difference between looking through an eyepiece in a telescope and looking at an image on a computer monitor. I kind of give the analogy of going to a live concert and listening to a CD. You know, there's something very different about those two different experiences, and it's the same thing here. So I would just recommend that if you're at all interested in doing this, you should at least try it out and continue doing it, because it's kind of, unfortunately, a dying hobby, just like listening to vinyl records or something. There's very few people do it anymore. But the beautiful photos of nebulae and galaxies fill the mind with the anticipation of seeing them firsthand. And yeah, you will be able to see them firsthand, typically, if you find them and you have a big enough instrument to see them. But again, the subtlety of what you're going to see in an eyepiece is going to be very different from the fantastic images we see some from, say, the Webb telescope today. But most deep sky objects aren't too small to see. I mean, a lot of people think a telescope magnifies. That's what they do, is they make things a lot bigger. Well, actually, the whole reason for telescopes typically is to turn up the brightness, so to speak, to collect light and concentrate it so that we can see these objects in the sky that are just too dim to see typically. It's not that they're too small. And sometime you might want to look through an almanac or star charts or something and just recognize how large these deep sky objects are. You might be surprised how many times bigger M31, the Andromeda galaxy, is than the moon, for instance. It's actually quite large in the sky, but the reason we don't see this beautiful big galaxy in the sky is because it's just so darn dim. So that's the first thing to be aware of when you're going to be doing deep sky observing. And anything deep sky, what we mean is beyond the solar system. So the planets typically anyway are going to be more than bright enough to be seen. So we need more magnification to see the small detail. But with deep sky objects, it can be a combination of both, but it's mostly their dimness. So one of the people I want to introduce here is Sir William Herschel. And he said something that's very appropriate. You must not expect to see at sight. Seeing is in some respects an art which must be learned. Many have, I guess that's covering my image here. Many a night I have been practicing to see, and it would be strange if one did not acquire a certain dexterity by such constant practice. And so, as Jeff can attest as well, practicing this art really makes you improve. And you might not think that that's happening, but it really does. The second and third time you go out and look through a telescope at the same object, your eye will learn how to see the very subtle details. And so instead of having a really nice contrast adjustment knob, we just have to practice our art when we're looking at things live. And so that's a very good thing to keep in mind. So tonight's goals, I hope to share a little information about how to get the most out of visual observing, a few pointers on observing projects, and why they look the way they do. Many times we look at these images that have been contrast enhanced and the color's been jacked up and all this stuff. And when you look in the eyepiece, of course, they don't look quite like that. And why that is, and expose some myths, and encourage you, of course, to try it. So congratulations, you're actually keeping amateur astronomy alive tonight at your SAS meeting. So a deep sky object is an extended object outside the solar system. So what I mean by extended is it's not a point source like a single star. It's something like a collection of stars or a gas cloud or maybe a whole galaxy outside the Milky Way. And they do not move relative to the background stars. So everything within the solar system, of course, moves against the background stars. These things are so far away that they are part of the celestial sphere, essentially. And they are very far away, typically. So they're at least out at galactic type distances. So we're talking about thousands, tens of thousands of light years away within our galaxy. And of course, outside the galaxy is hundreds of thousands to many millions of light years away. So one thing that many people do, and unfortunately, I've kind of lost my logs over the years. I have pieces and fragments of log books, but nonetheless, I would encourage you, if you're just starting especially, is to keep a log of your observations. So you can look back and say, well, gee, 3 years ago, we saw the same galaxy. And what were my notes on that? That can be a very fun experience as well. So the things you'd want to include in an observation logbook would be the times, dates, locations, conditions, and what kind of telescope you're looking through, eyepiece. And so you have some sense of being able to compare apples to apples, so to speak. And for each object, you want to record the name, the number, if it's a Herschel object or a Messier object, the type, and of course, there's many different types of deep sky objects, but mostly they're nebulae, star clusters, and galaxies. The size of the object in the sky, and the brightness. Typically, you want to record, say, the recorded brightness in some kind of a source, and then how bright it is to you. So they're both of those things. And then the magnification used during your observation. And they want to make any notes you might see that's a little different from other objects, like any instances of color, bright stars in the field, and anything else that sets it apart from other objects, because there's very tiny dim galaxies. You're going to be looking at many of those. But if there's anything that makes that one dim fuzzy stand out from the other ones, that's always a fun thing to record. And so let's look at the different types of objects. And this might be old hat for many of you, but for the new people, it probably needs to be recollected. So an open cluster of stars, that's usually a loose collection of stars, and they're usually gravitationally related to one another. And these clusters, there are two kinds of open clusters. There's the gravitationally bound, and then there's the unbound ones. The unbound ones are where the stars have formed usually together out of a gas cloud, and then they will eventually meander away from one another like brothers and sisters do after they grow up. There's also the gravitationally bound open clusters, and I actually have an example of that here in a few seconds that we'll show you. And so open clusters usually range from a few to thousands of stars. That's kind of the range of numbers. And for a log, you'd want to try to record the estimated number of stars. If there's way too many to count, you can give kind of just a ballpark figure if you want. And the richness is how clustered they are, how densely clustered are they. And any unique condensations, like, well, there's a whole bunch of them in the left-hand side or maybe towards the east, you might say, in the eyepiece, and any particularly bright ones that stand out. And one of these clusters, I don't have an image of it, but it just reminded me of the owl cluster. It's got about 6 or 7 brighter stars that kind of make the outline of an owl. That's kind of cool to look at. So here's an obvious example, the Pleiades star cluster. It's also known as M45 in Messier's list. And I don't think I talk about Messier anywhere else. I might as well just mention Messier observed with his telescope from Paris, France in the late 1700s. And he was particularly interested, as most astronomers were at the time, to find comets. And comets were very fascinating to them, and the way that they would change their display as the orientation between the comet and the sun and the earth would change during their close approach to the sun. And so many astronomers love to find comets because the first one to find it got to name them after themselves. So that was a big reason that Messier was looking for these comets. And so comets are basically like a relatively small, planetarily speaking, maybe a few miles across, and it's like a dirty snowball in composition. But when this very cold snowball-like object comes close to the sun's warmth will cause that ice to sublimate or turn directly into a gas. And if it's a relatively large comet with a lot of volatiles, that's things that want to turn into a gas when they warm up, and they can become very large and spectacular in their display. A lot of them never really develop much interest, I guess, beyond just a dim fuzzy. But the ones that were spectacular, of course, you'd really make quite a name for yourself if your name was attached to it. So when they would be looking for these comets with their telescopes, they were very eager to do that. And so Messier was so good at finding these objects, he started to come across these same objects over and over. And the way they would tell these things as being comets is that over, say, a night or two, they would move their position in the sky. So they would take very good notes about what they saw and where it was relative to some bright stars. And if it didn't move, they would say, oh, shucks, this is not a comet. And Messier started making a list of these things that were not comets, but they were dim, fuzzy spots in the sky. So as he made this list, he kept publishing groups or tranches of these objects in the newsletters. And his first list, I believe, was 45 objects. And so this was number 45. And I think he was scraping the bottom of the barrel there to get to some even or odd number in this case, but a nice number of 45 in this list of objects that are not comets. And so it's kind of ironic how he was looking for these objects and wanted to make sure he didn't report a non-comet, but actually that list is by far his lasting legacy. None of his comets were really much to write home about, I guess, or keep in our records. But anyway, so this is number 45 of those, and this is an easy open cluster, even to the unaided eye, because the bright stars in this image are around 4th and 5th magnitude. So this is very more than bright enough to see with the unaided eye. Most of you have probably seen this. Use binoculars is probably the best view of it, really. And they are covered or enshrined with this wispiness of nebulosity. And actually, most of this is not gas. It is mostly very fine dusts. And that fine dust is reflecting the blue light from these very blue stars. They're mostly O and B type stars, which are put out most of their visible light in the blue part of the spectrum. And that's why they reflect this blue color. But they're kind of like the swaddling cloths of these stars, because these stars are on the order of just a few dozens of years, millions of years, or yeah, wait a minute. I'm getting confused here because I just gave a talk about this for some other reason. But these stars are only on the order of a few million years old. So they're very young, to say arc star, the sun, at about 4.5 billion years old. So let's move on. This is an example of another open cluster. I can't remember which one this is. This is an old image I got from Jack Newton. Some of the old guys there might remember that name. So let's move on here. And now next I want to talk a little bit about globular star clusters. And so globular star clusters should make you think of a globe, not a glob, which many people suggest that, but their pronunciation. But a globular star cluster is like a sphere. I mean, and that's exactly what they look like in a telescope. And so it's a sphere of stars, but these usually are on the order of hundreds of thousands of stars. They can even range up to a few million stars in a very compact globular collection. And of course, they're gravitationally bound and will be forever. And I forgot to mention there that the Pleiades star cluster is one of the few gravitationally bound open clusters that there are. So we can have similar log entries if we're observing these in our logbook, but you want to add in information on the central brightening. It's surprising because most images don't give you the idea of very concentrated central brightening. But visually, when you look at these objects, the centers of the globular star clusters typically goes up to nearly a point bright source at the center. Not quite if you're using a lot of magnification, but they do vary significantly on just how bright they get towards the core versus other ones. And so that's something that you definitely want to record in an observation. And again, it's not as obvious in a digital image. But here we go. This is probably a digital image itself. But in the telescope, you'll notice that this very center will appear significantly brighter. But your eye is very good at having a wide range of contrast and brightness. And so it will actually see that much more apparently in this object's compared to, say, these digital images. But nonetheless, you probably won't see much color. Most of the time, these objects are just too dim to register with our color senses in our eye, which we'll get to a little later. So nebulae would be the next large category of objects we look at in telescopes, and that's a body of gases typically that emit or obstruct light. So this will cover both what we call bright nebulae and dark nebulae. So they're usually mostly gases. However, in the dark nebulae, and even in some bright ones, we have some dust as well, but it's mostly gases that do this. It's usually associated with stars that excite or get blocked by the nebula. And so those gases get excited. If they're nearby very hot stars, they will be excited typically by the large amounts of ultraviolet light, and then they will get rid of some of that energy by emitting visible light. And so that's typically how we are able to see them. So these objects usually respond well to narrowband filters. So if you ever use a deep sky filter or an O3 filter, and most of these filters, they're made such that they allow certain wavelengths of light to get through that filter and block many of the other wavelengths. And so it gives you the impression that the object is brighter through the filter, but in reality, we're only darkening the background scattered light, say light pollution, for example, or it could be even moonlight. So you want to record things in a logbook, things like color, if there's any to be seen, knots or concentrations, filaments. Of course, if you've ever seen the Veil Nebula, there's plenty of that. Maybe a central star, if it's a planetary nebula, that's one of our favorite kinds of objects to look at. There's plenty of those to be seen. Any associated star or star clusters, and if you used a filter, anything like that, of course, along with magnification, I like to record that kind of information. So here's an example of a famous, what we call emission or bright nebula. And so most of this reddish color is due from emission from hydrogen gas. So there's hydrogen gas in this nebula. That hydrogen gas absorbs ultraviolet light from nearby very hot young stars typically, and then it re-emits it in the visible wavelengths. And a lot of it's going to be emitted in one of the bright red lines of hydrogen. And here's another kind of emission nebula. The planetary nebula is also known as the ring nebula. It's pretty obvious why it's called that. And in this image, you can see the central star pretty easily. With the unaided eye in a telescope, that central star is actually a lot more difficult than you might expect. The central star is a white dwarf in this case, and it puts out a large part of its energy in the ultraviolet, which we can't see with our eyes. But typically, these imagers will detect that very easily, and so that's usually very apparent in digital images. Here's another one of my favorites. This is the Dumbbell Nebula, and I picked this particular image because there's a lot of the green nebulosity. And planetary nebulas, because they're from an evolved star, they have a lot of other gases in them, aside from just hydrogen. And in these planetary nebulas, oxygen is a common one, and oxygen has a very strong emission line of green, which is from the oxygen atoms, which again absorbs ultraviolet light and re-emits much of it in the visible wavelengths. The red can be hydrogen, but also in planetary nebulas, much of it can be nitrogen as well. And if we look, can you see my pointer here? Nobody's saying anything. Is anyone seeing?
Yeah, I can see it.
Okay. This notch right here, kind of V-shaped notch, that is very apparent. Whoops. Let's go back. This is very apparent in larger telescopes, I've noticed. Have you seen that a lot, Jeff?
Microphone. Yes, both sides of the dumbbell, but to me, the thing that stands out is the football.
Yes, the overall shape is much bigger than what's called the dumbbell. The dumbbell is kind of in here. It's kind of like an apple core right here. But then on some of these deeper images, you can see these extensions in the green that really fill it out. And instead of just an apple, it looks like a football. It's so enlarged on that axis. But I notice on one side, it's more apparent than the other. But yes, you're right. There's another side here. It's more diffuse on the other side. But this one is just really, on some nights, it can be very apparent. And your eye is mostly going to be detecting that green color. Digital instruments are going to record the colors much more faithfully, whereas our eyes are made in such a way that we kind of get a distorted view of their what they look like in colors. And again, in the telescope, this is probably not going to be bright enough to really cause you to be able to see this greenish color, but that greenish color is actually going to be easier to see than this reddish color right here. And so when you see this at night, you're dark adapted and your eye is used to looking in very low light conditions, this notch here really stands out. And as Jeff mentioned, there's another one that's kind of symmetric in the eyepiece, but anyway, that's kind of a cool one. So that's the dumbbell nebula. And this is a different kind. This is a supernova remnant. This is, of course, the Crab Nebula, which is the first object on Messier's list. It's in Taurus, the bull. And unfortunately, you don't see this really gnarly looking network of filaments here, because if you notice what color they are, the reddish color, your eye is just not going to pick that up nearly as much as the greenish color. And it looks more like a lazy S shape in the sky. And it's just kind of more cloudy than anything. Those red filaments just do not show up in the eyepiece nearly as much. So don't expect to see that. So that's another example of how these can look very different than what you might expect. And this is another supernova remnant. This is the Veil Nebula, actually just one small section of it. But it's probably the most interesting and part of the brightest part of the Veil Nebula. And you can see how filamentary this really is. And this, I'm just trying to get an idea here. Probably the right 2/3 of the screen is one eyepiece full with my lowest power eyepiece. So I actually have a scroll file that I use with the drive system that actually traces this out. When all you have to do is sit at the eyepiece and wait for the telescope to actually scroll around the entire complex, which is pretty fun. So now we want to move outside our Milky Way galaxy. And so other galaxies are, of course, large collections of stars, usually billions to even a few trillions of stars per system. And so there's the different types. There's the elliptical galaxies, which is by far the most common. They run about 70 to 80-ish% of the galaxies out there. Another common one are spiral galaxies. And of course, that's typically most deep sky observers' favorite type of galaxy to look at because they have such a wide range of shapes and orientations. And there's the irregulars, which is kind of like everything else. And then there's also a subgroup we call gravitationally interacting, where they might have typically very nice spiral structure, but then it's distorted because they're interacting with another nearby galaxy. So the elliptical galaxies just look like a football or an egg. If they have any shape at all, a lot of times they might just be round with very little hint of shape. And so they can, though, have differences between them. They're not just a fuzzy little spot. Again, as you learn how to do deep sky observing, you're going to get to the point where you're going to be able to immediately say, oh, this one has a really bright central core, and they may even have what we refer to or make notes as a stellar nucleus. Sometimes the central brightening is so small and so sharp and bright that we'll actually record it has a stellar nucleus. So we don't mean that that's one star there, but it looks similar to a bright star right in the center of the galaxy. And so some galaxies have that and many others don't. So we can also look at fields of a whole bunch of galaxies at once. And so the Virgo cluster is probably the most common place where you can see that, where you can see maybe a dozen galaxies in one eyepiece full. So you kind of want to record for these things their shape and orientation, if they have any, central brightening, as I was talking about, apparent stellar nuclei, and etc. So anything, again, that would make that any different than the other dim fuzzies, because a lot of times if you're just starting out, they'll all look pretty much the same, but you'll be able to pick out things that make it different from other ones as you're going along. So this is one of the favorite spiral galaxies that we look at. It was the first galaxy recorded as having a spiral structure. And that was Lord Ross, I believe, with his 72-inch telescope. And he made a drawing of this. It's fairly well known. And Van Gogh actually saw that. And it was his inspiration for painting that Starry Night image where they had the swirls around the bright stars. And so that's kind of something that's most people don't realize. A lot of people have suggested that he had some kind of eye disease or something, but no, he was just inspired by this drawing that Lord Ross made of the Whirlpool Galaxy. Of course, that's what we call it today. And so the spiral structure is pretty apparent. Some people claim they can see it with like a 4-inch telescope or something, but I have a feeling they've been imbibing in some substances that are typically illegal, I think. I usually need to see through about a 12-inch telescope before I can say, yes, I definitely see a spiral structure. But if you can see it with a smaller one, that's great. Not trying to make fun of you, but you can see that this one is also technically gravitationally interacting with that smaller galaxy to the left there. And this is one of my favorite objects. If it's in a good place to view it at all, I probably will be looking at that sometime in that night. So here's another image. This is a spectacular digital image, but nonetheless, it shows another similar to the M51 there, the Whirlpool. And so you can see that these come in quite a few different styles. And so this may even be a Webb telescope image. Those diffraction spikes in the stars look familiar. So I just found a nice image of a spiral galaxy there. This is another one of our favorites to look at. This is NGC 4565. It should have been bright enough for Messier to have recorded on his list, but he did not. And this one is an edge-on spiral galaxy. So you can see this is more face-on, and these objects aren't just balls or footballs. They actually look much more like a pancake. And so when they're face-on, they look like this, and when they're edge-on, they look like this. And so this one shows that classic edge-on dust lane is typically what we call it, but it's more cold gas that creates most of this, what we call dust lane. The dust is some of it, but not certainly all of it. It's much more actually cold gases. So anyway, this is really cool to see in a telescope with the visual observation. It does fade off a little faster than you see in digital images. Usually they have the ability to stretch their contrast and make it look a little more filled in, but it looks a lot more needle-like in the eyepiece of a telescope. And if you have a big enough telescope, you'll be able to easily see that dark lane right through the middle of it, bisecting it there. So very, very cool. And so this has got quite a wide aspect ratio compared to its thickness. So you can see there, it's probably something on the order of 20:1. So magnitudes are used to describe brightness. And so if you're new to astronomy, you'll certainly come across this term to describe brightness, and we use what we call magnitudes. But there's some quirks to the magnitude system that you'll just have to get used to over time. It's not a very intuitive system. So Hipparchus originated this scale for brightness of stars in about 150 BC, or BCE, I guess I should write. So he obviously was only using unaided eye observations. And again, I already mentioned, I think the eye works very logarithmically. And so we can see very bright objects on down to very dim objects. Matter of fact, I don't think there's any solid state detectors that have the wide range that human beings do. And so in this scale, though, the smaller the number, the brighter the star. And that's kind of an artifact of what he did. When he looked at the night sky, he wanted to make a list of the brightest stars. And so the absolute brightest stars in the night sky, he would write down that they were stars of the first magnitude. Okay, and then the stars that weren't quite as bright, but still pretty bright, he said these are stars of the second magnitude. So this is where we get the scale going backwards, where the bigger the number, the dimmer the object, right? So anyway, he had it on up, I think, to the 5th or 6th magnitude. And so the biggest number was 5 or 6. Those were the stars that he could reliably still find. If he thought he saw a star somewhere and couldn't reliably find it again, he did not record it. So again, the brightest stars were of 1st magnitude, the dimmest were of 6th magnitude. And so Galileo later on, quite a bit later on, extended this same system. And so he took those 5 magnitudes between 1st and 6th magnitude, and he said that in reality, that's about a brightness difference of 100. If you work that out mathematically, that's about what it is. And so he kind of just then defined it as that to make it a little more scientific. So each magnitude represents a difference in brightness of about 2.51, or about 2.5 times brighter. So when you look with your eye at a 1st magnitude star and a 2nd magnitude star, the 1st magnitude star is going to look brighter. There's no doubt about it. But does it look 2.5 times brighter? I don't think anyone would say, oh yeah, that's 2.5 times brighter. But in reality, it is. That's an artifact of our eyes working more on a logarithmic kind of scale. So that doesn't really look that way. So if you multiply it out, the difference in brightness between a 1st and 6th magnitude star is a factor of 100 times. And our eye does not record it as 100 times brighter. But that's just the way they work. So these are just objects that have been extended far beyond what Hipparchus did. So the sun in the sky is minus 26.7. The full moon is about minus 12.5. Venus about minus 4. Sirius, the brightest star in the sky, it's of course crept on the other side of the 0 in the system. So it's a 1.5 minus. The Big Dipper stars are right around 2nd magnitude. Okay. And the dimmest naked eye stars you can see are around 6 to 7. If you're on a really, really dark night with great conditions, 7 is not out of reach. But that's about how the scale works out. So then with a 50 millimeter objective in a binoculars or telescope, you can see down to about plus 9.5. So we can stretch this even more. So a 6-inch telescope can see to about plus 12.7. An 8-inch about 13.3. That's right about the brightness of Pluto, for example. And a 12.5-inch telescope about plus 14. 20-inch scope about plus 15. So you can see here that you have a pretty big jump in the size of the telescope just to gain one more magnitude there. And so a 30-inch scope, it's not even a full magnitude, gets down to 16. And a 41-inch telescope, that's still not quite 17th magnitude. And Hubble is around plus 30. That's an incredible dimness that it can record. Of course, that's when we take exposures that last a whole week. So imagine using a 2-meter telescope in the depths of space for over a week exposure time. That's how it can get down to plus 30 in brightness. So the magnitudes of these deep sky objects, though, that's not the only thing we have to worry about. They're still somewhat misleading, because you can say, well, you know, that galaxy, it seems very bright according to its magnitude, but you can have a devil of a time trying to find that darn galaxy. And that's because it's really large and diffuse. That brightness, as it's recorded in the catalog, is recorded as if all the light coming from that galaxy were in a single point like source, like a star. But if you spread that out over a surface area, it's going to be very hard to see with the unaided eye. Not that it's impossible necessarily, but it's going to be a lot more difficult than what you might expect. And that works the other way as well. Some objects have a very low brightness, but they're very easy to spot in a telescope. And that's because they typically have a very small surface area, and they're not having to spread out that light over a very large area. So an object in that category would be like the Ring Nebula. It's got a very low, what is it, over 8th magnitude? I can't remember off the top of my head, but it's a very small object, and so it's actually pretty easy to spot. What was that? Okay, so M33 should be really easy. It should be easily naked eye at +6, but it's a known difficult object. And that's because it actually has quite a large size in our sky. So that 6th magnitude star-like light has been spread out over a pretty big area. And so it's actually a very diffuse object. And this is M57, that's the Ring Nebula. It's usually recorded as 9th magnitude, but it's usually really easy to see in a small telescope because it's not much bigger than a star. So again, that difference is surface area. So this is one of the main things I wanted to emphasize to you. So here is an image of M33. I selected this one because the contrast hasn't been jacked up. And you can see it just looks like a brightening of the night sky glow. And that's kind of the way it looks in a telescope, unless you're trying to use a filter or something on it. And I forgot what I was going to say. It's old timer's disease. Okay. So deep sky objects are dim due principally to their tremendous distances. So we must also keep in mind the size of the deep sky object. So after a while, you get really used to it. Hey, this is going to be a small planetary nebula. And so you get a good idea of how dim of the objects you can see of those. And well, these are some larger nearby galaxies, and the magnitude estimate is going to be spread out quite a bit. And so you get an idea as you're looking through lists of objects to say, look for. And so when recording brightness, take into account, again, the size and the type of object it is. And it just takes practice to enjoy the subtle yet sublime beauty of these objects, taking into account their distance and true nature. I mean, if you're looking at a dim, fuzzy spot, this little dim, fuzzy galaxy, well, if you realize that it's 120 million light years away, well, that might make a difference to how you judge its beauty, right? So, of course, now the sky background is going to be one of the biggest killers to visibility of these large diffuse objects. That's why if you're going to do visual observations, you really want to get away from unnatural light sources and even some natural ones like the full moon. That's a really huge contributor to light pollution and something we can't do anything about. So it's important to try to minimize its effects as much as we can. So even a slight increase in contrast can make all the difference. I've actually taken my telescope and did some observing runs in a suburban location that actually was pretty decent for being close to town. And the very next night, and the conditions are practically identical, and I just go to a darker site. It's just amazing how much the difference is. And it's more than worth the extra gas money and time to get away from city lights. And higher elevations usually are also a help. It's just you get out of the denser part of the atmosphere where light can scatter more. And so you're closer to the stars as well. When people complain about the height of the ladder they need to climb to look through my telescope, I just remind them that you're closer to the stars up there. So there's something that astronomers will talk about, the quality of the observing conditions known as seeing. And that's the quality of the clear sky. Of course, if it's totally cloudy and the objects are all obscured, there's no measurement of seeing, at least to observers. But there's actually comes in two different types. And so we have transparency, that's how clear the air is, and the steadiness of the images that are produced after that light has passed through the atmosphere. So we have two different factors here, and they're not quite independent. there's some correlation, but not completely. The transparency is usually much better in cold conditions in the winter. But the steadiness or seeing, which is, of course, we kind of use it for both terms, but if you want to kind of talk about it in contrast to transparency, then we talk what's meaning the steadiness of the view. And so when you look in the across the desert highway and you see things shimmering just above the freeway, that's what's causing that steadiness to flicker and wander and jiggle, kind of like. And it's just like in the winter, you can look out at the stars. A lot of times I'll look up at Orion, but I'll notice that Orion is twinkling a lot. Even though it's pretty high in the sky, there's a lot of twinkling going on. But if I see the summer Milky Way constellations, they typically don't twinkle nearly as much. As the warmer weather usually steadies down that seeing part. And but usually the transparency is less in the summer. And of course, these aren't hard and fast rules. These are generalizations, but usually you have very warm conditions, then you usually have fairly good steadiness, but the transparency usually decreases and vice versa. So transparency is a measure of how clear the air is. That's pretty easy to think of. And the main offenders to transparency would be thin clouds. I mean, when you see especially when I'm observing, you can't notice a lot the very thin clouds that might be moving through. But after the sun comes up, you can see these thin wispy clouds that you were looking through all night. But also any sources of haze, smoke or fog or dust, any of these kinds of things can greatly affect your transparency. And so that'll affect your ability to see the fuzziest, dimmest objects. You want transparency to see the dimmest objects possible. And so again, it dims the objects and it reduces contrast, because those offenders there, they will scatter any other light, even if it's natural light. It'll scatter any other light and make it harder to see the object of interest. And so that can be very bad for deep sky observing, which is specifically what we're talking about tonight. And then there's the seeing or steadiness of the view. And that's, of course, important as well. And it's usually overall better in summer. And usually poor steadiness and poor transparency occur one at a time. It's usually one or the other. You can't have both at the same time, which you might as well pack up. But this causes the images to apparently boil, or the stars won't stay nice, tight points. They'll kind of swell and kind of jiggle around or wander around in the eyepiece. And of course, fine detail will just be destroyed due to poor seeing. Okay, this usually is what planetary observers are talking about when they talk about seeing. So that's one of the reasons why that name is used kind of in a broad sense and in a narrow sense as well. Poor steadiness will affect high power observing more so than low power, but it doesn't rule out good deep sky observing. When you're looking for larger fuzzy galaxies, this won't have nearly the effect on it as poor transparency. Hopefully that makes sense. So now we're going to switch gears and talk about the eye and how the eye interacts with these low number of photons coming from these very distant objects that we're trying to look at. So this is just a cross section of the eye seen from above. And so I won't read off all of these labels, but there's a few things I want to point out. The inside layer of your retina here, that's what this is. And that's where the light sensing happens in your eye. Okay, your eye is a complete eyeball and it's filled with this fluid. And you can have little weird things within that fluid as well. And if you're nearsighted, you might know what I'm talking about. And then there's this almost a crystalline lens here. And then we also have the cornea. So most people think the cornea is the lens. It's actually two separate objects. But between these two lens-like apparatus, it will form a focused image on the backside of the eyeball. And the inside edge is where the retina is, and that's where the images then are sensed. And this right here along the visual axis, that is where the fovea is. That's the center of your vision. And most people don't think a lot about it because we're just used to it, but if you notice, we're always looking directly at what we want to look at. You don't look at something way off axis from it and expect to be able to read words, say, way off axis. Because of the concentration of light sensitive cells at your fovea or center of vision, that's what allows us to read, especially fine print. So if you've ever tried, you can hold some fine print way, good 5-10 degrees off axis from the center of your vision. You can't read that. You can tell that there's text there, but you won't be able to read it. And so it's very important. That's why when we're reading a book, say, we're scanning line by line, right? You don't just look at a page and, oh, I read it. No, you have to scan each line individually. And so that's one thing that takes place, of course, when we're observing, and something to keep in mind. So yes, we have light sensitive cells over the entire interior of our retina, but they're not evenly distributed. And I'll show an image, kind of a diagram of that a little later. Let's see, what else we want to talk about. So this is the optical axis of our eye, but then on the other side of the optical axis is actually this place where the nerves exit from your retina to go to your brain. And so at this spot, there's no light sensitive cells at all. So this is what is traditionally called the blind spot of the eye. And so most people, in most times, I guess, they don't notice that there's a blind spot in our vision. But with two eyes, your brain can easily then fill in the blind spots from the other eye. And so we typically don't notice it, and we're used to it. But it really is a blind spot there. And of course, there's plenty of places on the internet nowadays you can look at these diagrams that will help you point your eye at one particular place, and then there will be another dot or an X or something, and it will disappear when your eye is placed in the right place, because the image of that dot or X will be placed where your blind spot is for that eye, and it literally will disappear. It's actually fairly large compared to what you might think. So that's something to keep in mind as well. And it turns out that there's actually a different distribution of the retina cells when we're talking about the differences between color and monochromatic images, and those cells that do the different sensing. So I'm not sure there's anything else that we need to cover right now in this image. So this is just a different view of the eyeball, this time from the side, kind of a 3/4 view. And of course, when we're observing very dim objects, we want our iris as open wide as it can be. And unfortunately, the iris does not open as wide as you age. So when you get to be really old, like over 40 or so, this will actually start to not be as big. It'll actually start getting smaller and smaller, unfortunately. Another thing is that the lens can get cloudy. Apparently, part of the reason is ultraviolet light will cause cloudiness to form within the lens. And at a certain point, they'll actually remove the lens and do a cornea, or what am I trying to say, that surgery that they do when they replace the lens. I don't know why I'm blanking right now. But anyway, many people report that they can see into the ultraviolet region of the spectrum once that lens has been replaced. So if you get to the point at which cataracts, that's what I'm trying to say. When you get cataract surgery, they replace that lens. And so if you get that lens replaced, you might want to look at the central stars of planetary nebulas. You'll probably notice that they're a lot easier to spot now. But anyway, move on. So there's two different styles of these light sensitive cells, and maybe you've heard this before, but they're called rods, and the difference between cones. And the rods are monochromatic light sensitive, and the cones are the color sensitive cells. But to get our color vision, we have three different kinds of cones. And so cones come in three styles, or they detect the three different primary colors, depending on which kind they are. And they permit, of course, our color vision. And they are mostly concentrated in the center of our vision. So they're very highly packed there. And they're very sparse, it turns out, in our peripheral vision. So most of our peripheral vision is monochromatic. Now, if you have very fine color details, that means the color comes in very tiny patches. If in your peripheral vision, those colors might be less easy to see or may even disappear completely. You probably won't notice unless you're trying to pay attention to that. because usually if you're trying to look at the fine detail, you point your eye right at it and see it. So that's how we deal with it. But just in your peripheral vision, it's essentially colorized with a relatively low number of cone cells. And so the way our vision works is a little more complex than most people think. It's actually quite different than a video camera, okay? Those cone cells don't work well in low light. One of the reasons is that they essentially, because they're only visible to one color of, or one primary color, they'll see, of course, less of the various colors that we see in what we call, quote, visible light. And so instead of seeing all the visible light that your rods see, you only see, say, blue photons with your blue cone cells. And so that's one of the reasons, but they just in general do not detect very low flux of photons or the amount of light coming through. They just are not nearly as good at detecting light when that amount of light is very low. So, and as I've already suggested, the rods, though, are monochromatic. So they don't convey color information at all. And they're not particularly dense anywhere, but they are just compared to the cones, they're more common in your peripheral vision. And that's where a term comes in that astronomers, observational astronomers use, of using averted vision. And so that's where we're actually utilizing the capacity of the rod cells to detect dimmer light sources. So you don't want to look directly at it. And so this I thought was an appropriate image. Only one person got that. Is that too old for the most of the audience there or something? So anyway, okay, I guess we'll skip that. I'll take that out next time. All right, so here we have the cross section of the eye in a diagram, and we can look at more close up what's going on in the retina right here. So as the light comes in through the eye and the lens system there, and it focuses the image on the back of the eye there on the inside edge, there's the retina. And then as we blow that up really big here, we can see that these are just other cells, epithelial cells is what they're called. And then these cells, these are the structures that actually detect the light. And there's also, then the nerves are actually attached to the top above the cells that detect the light. And so the light comes in and forms the image here, and this is where it should focus it to be correct. And then, so it's slightly out of focus in here, but it's so close to these other retina cells that you basically don't see any of this other stuff. And so there you can see not a comb cell, but a cone cell, okay? But maybe that's to help us register, that's kind of sounds like cone. Anyway, so here you can see red, green, and blue cone cells. And so these nerves actually attach to them on top of, and then they send their information out. And then, so all these connections to those cells has to go out through this place where we have our blind spot. So that's where those go off and connect to the brain. All right. So at least in mammals and some other species, I think as well, I remember, right? Sorry, just had to get a drink. The retina is inverted. So what we mean by that, let's go back to the image, is that in many other animals, these cells are oriented the other direction, so that the nerves actually connect to the backside and then they go off to the brain. And people have complained that this is not a very good design, but it turns out this design is actually better, because these cells, and this is kind of one thing that blew me away when I first read it, is that they are huge users of sugar. To work, these things need to have a high concentration of sugar. And in this orientation, this is the best way to get them their energy source, a constant energy source, so that they can work at their top efficiency in that way. And it turns out that this design is just actually better, not worse. So that's kind of an interesting thing. And again, it allows direct contact with the sugar and the oxygen from the bloodstream. And these cells are like muscles, and they require these things constantly when they're used. So when you're out observing, that's not the best time to be on some kind of a fast or something. It turns out you want to be eating those candy bars and giving those rod cells, especially, the energy they require to work at their best. So you might want to remember that while you're observing. And also other things is don't smoke or drink alcohol. That will decrease O2 getting to your retina cells. And breathe deep, and don't stop breathing when you're looking. You know, a lot of people, even I had this trouble at first. You almost want to stop breathing when you're looking through the eyepiece, but that's not what you want to do. You want to be just breathing deeply and slowly while you're looking. And so again, candy is helpful. That's just a ready source of sugar right to those cells from your blood. So this is an actual image of what's going on there. So these are the actual retina cells, these long rod-like structures. And these are the cones down here, which is kind of interesting. And so this shows kind of the density of your rod cells versus cone cells. And so this is just cone cells, I believe. And so this is looking at, and this is the center of your vision. And I can't remember what the scale is here. But anyway, you can see that there's quite a bit more concentration of cone cells at the center of your vision. I already mentioned that. It shouldn't be a surprise. And then here we see the entire retina, and there's the optic nerve head, which is essentially our blind spot. So here we can see that's the center of our vision. There's a high concentration of cone cells there, and they fall off rapidly to our peripheral vision. Okay. And so this is just a different way of diagramming that, but it also includes the rods. So here you can see the cones and the center of your vision at 0 degrees here is the cross section. It's concentrated the very most at the center of our vision. That, of course, should be obvious, I think. But notice how the rods peak out a little ways away from the center of your vision. Out here, about 10, 15 degrees out, it peaks in the concentration of those rods. And then they fall off to the edges of your peripheral vision. And so this also shows essentially a very similar thing, but it's not the number of cells, it's how sensitive the eye is at those different areas. And so this is just showing why that should be. This is just more concentration of rods. Of course, we'd expect there to be more ability to see dim light. And so this is actually, when we're looking at very dim objects in a telescope, this is where we're going to be wanting to capitalize on when we look through a telescope. So it's not going to be looking directly at it. I'm not saying you never do that, but this is just in general thing of why this averted vision works. And we'll talk a little more about that in a minute. But keeping your eyes in the dark for an extended period of time is also very important. After 20 minutes in total darkness, your sensitivity is about 6,000 times more. After 40 minutes is about 25,000. So when we talk about being dark adapted, that's what we're talking about. And so when you want to get dark adapted, you need to have your eyes in near complete darkness to get them to turn up their sensitivity to light to these levels. And of course, it's decreased when in a bright sun, and that can last for up to 2 days. So don't go to the beach, especially without your sunglasses on, that the day of your observations that you're going to do that night. So yeah, you should keep your eyes protected from bright light for up to 2 days before you want to go out and look. And especially also ultraviolet light is a killer as well. So you should wear UV blocking sunglasses as much as you can. And so this is a diagram of that dark adaptation. So here's the cones. These are the color sensitive cells in your eye. And notice that this only gets a little over 100 times more sensitive to light there. So that's -10 to the -2. That's roughly about 100 to maybe 500 times more sensitive to light over time. The rods take longer, but look at how much more they get dark adapted. So here we're talking tens of thousands of times more sensitive to light. So it's just an amazing amount of dark adaptation our eyes can do. So the eye looks like a camera and can even do time exposures. This is something that seems controversial, but within the research community of biologists is not controversial. The dark adapted rods can integrate. That means essentially like take an exposure. It's not, they're not working continually instantaneously, but in compared to daylight, we can go from 1/10 of a second over which that those cells can absorb a photon and pass it on to the brain, up to 6 seconds. So yeah, when you're looking through a telescope, you want to keep some of this in mind. So You want to not look directly at the object, at least not all the time, because there's other things that you might be able to see there by looking directly at it. But then you don't want to have your die using your averted vision and having your eye dart around in the eyepiece a lot. That's not going to help you to see the dimmest it can possibly see. And I've read in some of the biological papers I read about these eyes when I put this together, that the evidence suggests that the eye can be capable of detecting single photons, which is unbelievable. Most CCD manufacturers would love to be able to record a single photon at a time. So when a dim object is located, you want to kind of stare at the scene in the eyepiece to see if more of it becomes visible. And so this might take some serious amount of time at the eyepiece. I can't tell you how many times people will look in a telescope and they literally just barely glance in there. I can tell that they actually detected what I'm telling them to see, but they literally just glance and then almost run away. It's like, I don't know what, if they're scared of something, that something's going to suck them through the eyepiece into the telescope. But anyway, yeah, you want to look at this stuff. I mean, imagine how much resources you put into getting out to a dark sky star party and look through a telescope. You want to spend your time at the eyepiece. So don't just glance, look, and really try to absorb as much as you can. And it might seem like low power would make dim objects brighter, and they do. Technically, lower power will make the concentration of light of those objects higher, and it should appear brighter. However, with the low resolution of your dark adapted rods in your retina, the bigger the object is magnified, the more visible it may actually become. I know this seems, oxymoronic, but it actually does work. In essence, more rod cells are available to detect that object. So this doesn't work for a star, because no matter what magnification you're using, it's still going to be the same size. But for an extended object like a small galaxy or something like that, that can make the difference between detecting it and not detecting it. And even though higher magnitude will make it technically dimmer. And noise reduction will mask small dim objects. And so your eyes kind of work just like a noisy CCD camera. Have you ever dealt with video cameras, even in dark environments? You'll notice that there's a lot of like sparkles in the image. And some of those are real, just random photons bouncing around, but much of that is literally electrical noise in the nerves, or in your video camera. It's just in your video camera. And when we're dealing with really low light, then we have to try to detect every single photon we can. And so there is noisiness even in a biological eye, and our brain filters that out. So we don't have to have some kind of algorithm to take that away. Our brain just naturally does that. And so when it does that, if you got a dim object that you're trying to detect, but it's so small that the intermittent light signal from that dim small object will actually not be constant enough to allow that light to be recorded by your brain. Your brain is just rejecting it as noise. And so this is another reason why the higher magnification actually helps to detect dim objects. And so if you've ever taken a book and tried to read it and turn off the light and try to read it, now if you have enough ambient light in the room, you might be able to see that there is text there, but you can't read it. Okay, that's the same thing going on here. If we're trying to look for the small little details in what we're trying to look at, our vision in the dark is just so low resolution that it's very hard to see any fine detail. And so again, higher magnification might, ironically make that more visible. And so I've actually done this, and you think that dim little galaxies, you actually see the most detail, if you can see it, at higher magnifications. Unfortunately, the higher magnifications are much more difficult to have or to use when the seeing is bad. So that's one of the things. So here's a diagram I tried to make of, say, a galaxy. You're trying to look at this galaxy, observe it, and make notes about it. But you want to keep the galaxy in the center of the eyepiece. That's usually best. But then put your center of your vision about 30 degrees away, opposite the direction of the eye that you're using. So that means if you're right-eyed, most people are dominant in one eye versus the other. So I happen to be right eye dominant. So I will actually avert my vision about 30 degrees to the right of the object I'm trying to look at. Now, again, my rod cell concentration very low here, so I'm not going to have really fine, detailed vision. So I want to use more magnification to kind of see that. And again, I avert the center of my vision away from the object I'm trying to look at, which seems difficult, and it's not the easiest thing in the world to do, but you do learn how to do that. And then remember that your blind spot is a little further along that same direction, about 15 degrees away from the center of your vision. So what about color? It looks like I've gone way too long here, Jeff. How are we doing for time? Am I too long?
We're still here. Don't worry about it.
Okay. So by the looks of color photos of these nebulae and even galaxies, disappointment awaits at the eyepiece. That's because our eyes are just probably not going to see those colors there. And several things add up to cause this. So we'll look at a few. As we know, light travels in wavelengths. They're kind of like a hybrid between a particle and a wave. And they travel at different wavelengths. And we, of course, perceive that as different colors, if we're not colorblind anyway. And blue is a shorter wavelength than red by a significant amount, it turns out. So you probably know all about rainbows and how you can make them with a prism or a diffraction grating. But here I wanted to kind of cover just a little bit about how these colors are perceived by us. And so here's blue. The blue wavelengths are at about 4,000 angstroms, I believe. And these are in, well, I can't remember now when I made this. But anyway, these are the wavelengths in nanometers. Here it is. And so 0.4 is the blue and about 0.7 is about the red. So that's the range of wavelengths we can see. And these are the corresponding colors. And so when we see an object that's very deep blue color, that means it probably is reflecting almost none of the other colors. It's only reflecting blue, or it's only emitting blue light if it's a emitting light. And so it will be mostly blue and very little of all the other colors. If you see something that's pale blue, then it's going to look something more like this, where there's a lot of blue present, but there's other colors that are just in lower concentrations. Does that make sense? So here's the difference between a deep green and, say, pale green. A pale green is going to have more green than anything, but it's going to have a mixture of other colors with it. And that's what makes it pale as opposed to a deep green. And it's the same thing as the red here. So when you see something that's very, very red, it's going to have lots of red and almost nothing else. And if it's just more or less red, then of course the spectrum will look more like this. You're going to have other colors mixed in with the red, giving it just a kind of a less deep red color. So we need to just look at very quickly how light is produced. And this is kind of like astronomy 101 here, because that's what we want to understand something about light when we're first studying astronomy. And so here we have a source. I think there we go. Here we have a source of light, a star or whatever. And when you look at it directly with your eye, you can then graph it out in color versus wavelength down here, and it will look something like this. So a yellow star, it's going to have a peak somewhere in the yellow or near the yellow on our spectrum. And so here's a diffuse gas, a nebula. But the way it makes light is actually different than just looking at a star-like source. Or you can also insert here an incandescent bulb, something like that. But when we're looking at a gas cloud, especially a diffuse low pressure gas, okay? A star is actually an example of a high pressure gas, right? But when we're looking at low pressure gas in space, and then it's energized typically with ultraviolet light, then it will emit light after it's absorbed it. And some of those photons will be emitted in the visible wavelengths where we can see it. But this is an example spectrum of, say, some kind of a gas cloud, mixed gases in it. And you'll see that it puts out light in very sharp peaks. And in some colors, there's almost no light emitted at all. That's why these nebulae in photos, a lot of times anyway, not all, will appear with very spectacular color. Okay, and so the different gases will be, of course, different colors. And so you can directly tell by the color what kind of gases are producing that light. Now, if you're looking at a star-like light source through a cloud of gas, okay, this gas will absorb away some of that light, but it can only absorb with the atoms that are in it very specific wavelengths of light. Those atoms can only absorb very specific wavelengths. And so if you can look between these two images, can you see that they're mirror images of one another? So we got a big peak here where this is emitting light, and a big dip here where it's absorbing that same kind of or color of light. And then these other peaks here are the reverse here. And so it's interesting. Either way, we can tell what these gas clouds are made of. And so that's part of why it's so very important in astronomy. We can actually directly tell what gas clouds are made of by looking at the light that they either make or absorb. And so that can be helpful to understand when we're looking at these objects in the night sky. Here we can see that the rods typically, now we've evened out their relative efficiency at detecting, but we're just trying to show that there's a difference between the peak wavelength of light or color at which they have their best efficiency. So the rods work the best. These are the black and white ones, but they are most sensitive right in the green area of the spectrum. The rods are a little more towards the yellow. I mean the cones, I misspoke. The cones are more towards the yellow, not by a lot, but it is some. But one thing I want to show you is that the cones are somewhat sensitive in the red, but the rods are less sensitive in the red. We can kind of take advantage of that and use red light when we want to look at, say, a star chart or something, or you want to write something in your notebook. That's why you want to use a dim red light. Your cones will allow you to see, and they're at higher density at the center of your vision, so that's good for reading and making notes. And these rod cells are going to be a lot less affected. So essentially, that's what I'm saying here. So from the previous diagram, far red colors are nearly invisible to the rod cells. So that's why we use red flashlights to illuminate things at night. And so we get to use our cone cells. Dim white flashlights and other colors will decrease the sensitivity of our rod cells. That's why it's so important to use red light. This is not an old wives' tale. I'm sure Jeff remembers Bob Lemley. He showed up at a star party. He had a dim blue flashlight. And he got the appropriate amount of strife over that. So as we look at a spectra of a nebula, this is the spectra of a planetary nebula. And here you can see the O3 is the highest peak. That's the most light is being emitted at this very green part of the spectrum here. Hydrogen alpha is in the red part of the spectrum. And so remember how I said the rod cells are not sensitive to far red? So unfortunately, our night viewing is going to be very insensitive to this hydrogen alpha line, which is so important. That's why almost all of the red nebulae is going to be very difficult for us to see compared to if it's being emitting in the oxygen 3 line, which is right here. So that's why these planetary nebulae are a big favorite of visual observers. They put out a lot of oxygen light in the green part of the spectrum, right where we are most sensitive to that kind of light. Okay, so I'll just quickly cover this one. So this is our wait a minute. Yes, this is the hydrogen alpha line in the red, and this is the O3 line in the green. And again, our rods are going, wait a minute, which one is the rods? This one. No? I guess I didn't review the slide enough to remember which one was which. Yeah. I'm not sure. Okay. Well, anyway, the cone cells are not going to see, are going to be usable for red, but of course they're not very sensitive in low light. So that's not very good. Okay, here's the blue. So it's the blue one here. I'm sorry. So this is the blue sensitive cones. Look how low they are in sensitivity. They're very low, which is really weird. So our green cones are the most efficient at seeing the stuff. And then here's our red cone cells. And so this I'm not sure what I was showing there. Anyway. But when we see a contrast between two colors with enough light where we can use our cone cells like stars, that's when double stars can be very satisfying to look at. So our cone cells get to operate. They're very happy because there's more than enough light concentrated here to stimulate your color vision. That's why contrasty double stars in color are going to be very fun to look at. So cones are used for color, so you might want to try lower power because they don't have the problem with the rods of being a low density, at least at the center of your vision. And you can look directly at it. So that's a big advantage to using your cones for observing. But you're going to have to look at just the brighter objects like M42, which is the brightest nebula in the sky. Planetary nebula are often green to blue. And so you might just pick up some of that green color because some of the cones, which again, even the most sensitive cones are the green ones, they're going to be used to their fullest extent with a planetary nebula. And think of pastel colors. You're not going to see, again, the bright colors of the photographs because they can increase the color contrast as much as they want. But when we're looking in the natural, they're not going to be all that super bright. Remember that we don't have all that much color sensitivity to start with at low light. So you might want to sketch objects, and this is something fun to do, but I never got into it. But it's pretty cool if you're artistically capable. So I'll just make some general recommendations. So in addition to your telescope and accessories, you want warm, comfortable clothes and shoes, a sketchbook if you want it, a hit list that's for potential targets, and observing project if you're working on one, star charts, objects to help you find whatever objects you're looking for. Be as rested and comfortable as possible, and don't exaggerate. Be objective. If you know an object's there but you just absolutely can't see it, don't say, oh well, I saw it. That seems to be a popular thing to do. So use photos to help look for subtle details. So what I like to do is I like to look at it first without knowing what it's supposed to look like, or at least, not fresh in my memory. And then I'll look at a photo of the object, and then I'll look again and say, well, can I see that particular detail? I wasn't looking for that, but maybe now that I know what I'm looking for, I might see more details that way. And so, and I always like to share the views and practice. So here's some of my observing stuff as I used to use it a while back. And you can get certificates from the Astronomical League. This is the Messier certificate. So this is from way back in 1984. This is my Herschel certificate. And so I'll just leave this page up for a little bit while I just see if there's any questions.
Yeah. Question, Dan. When you and I were going to Table Mountain, I'd get loaded up on peanut M&Ms and hard sugared Mountain Dew, thinking that's going to get me through the night. Then I'd have scintillation in my vision. So as I got older and more diabetic, I kind of knocked that back. And I noticed that if I don't drink caffeinated fluids and eat a lot of sugar, I lose that scintillation. Is that a real thing, or is that just my psychology?
I'm guessing it's real. There is some of that scintillation that's just natural. And again, our eyes seem to just remove that. It seemingly knows that there's going to be noise. And so if it's just random flashes in your vision, typically your brain is just going to smooth that out. What is interesting as well is that when the astronauts went to the moon, they reported when they were outside of the Van Allen belts that they would have flashes in their visual field, and they theorized that was cosmic rays hitting their retinas or close to their retinas.
We went on Sophia, and we did a cosmic ray experiment up there. But one thing we didn't do, I don't know if you did or not, was close our eyes and see if we can see that. Yeah, we didn't observe that.
Yeah, I've only heard of the astronauts in deep space being able to really see that.
Yeah, we were still inside the Van Allen belts. We weren't outside of the magnetosphere like those guys.
Unless you're flying high.
Anybody else got any questions they want to toss out here?
Hey, Dan, I have a question for you.
Hi, Tim.
Hi, excellent presentation. Thank you so much for the information. Excellent. You mentioned narrowband filters, moon filters, O3. Have you ever experimented around with just different colored filters for bringing out different features of certain objects?
I haven't done too much of that, but I know that the only people I see using them typically are planetary observers. The different colors will bring out some features,
Right.
but they are definitely broadband filters. I mean, they're nothing like a narrowband filter.
Right, you're just coloring all the light that's coming through the eyepiece.
Yeah.
A certain color. And then my other question was, you talked a lot about and educated as well on dark adaptation and the sensitivity of the eye. Oftentimes we'll be out there and we're, an hour into a viewing session, we're nicely dark adapted. And for whatever reason, we get a flash of white light, car headlights or whatever happens. Do you believe that that real short burst of white light is actually going to kind of ruin that dark adaptation and you have to start all over again? Or can you tolerate a little bit of white light without suffering much from it?
Yeah, that happens all the time. It seems to be a relatively short-lived phenomenon. But it definitely does affect it for the next 10 minutes, I would say. But you do, of course, get back to that high efficiency relatively quickly. So you want to avoid it as much as you can, but it's not like you have to start all over. It's nothing like that either.
Certainly. Well, thank you very much.
Sure.
So Dan, between something you said and something Tim said, that made me think of something else. Back in the day when we would hypersensitize film, the idea was that when it got hit with the first photon, the silver particle wouldn't react. It always took the second photon. So you'd either gas hypersensitize it to free it up to activate with that first photon, or we would light sensitize the film by flashing it in a dark room and then taking it out to the observing session. Now I'm wondering if you were talking there about how they have decided that it is possible for the eyeball to actually respond to one photon. So this makes me think that maybe a flash hypersensitization might actually work in that area, or am I just weird?
Yeah, I don't think so. I mean, I can't speak definitively, but the way that silver salts react to light, it is a two-step process for it to register a photon, or to actually change chemically. And so it does need a two-step photon thing. And so usually with regular photography, 2 photons is no problem. But yes, in this case, that flash sensitization is very possible. And then what the hypering did to film was it would make it so that a longer time can elapse between those 2 photons, turning that chemical switch, or whatever you want to call it there. Boy, I'm just blanking on the word I want to use here. But that chemical change that occurs when it's exposed to light, it's a 2-step process. So there's 2 photons involved. And yeah, you're right. You could pre-flash the film. It's a very small amount of light, and you also want to do it very uniformly on the film. But then when you're out observing, I think it was the hydrogen would help lengthen the time between the 2 photons could come in and then be sensitized, allow the film to capture that and chemically change. So yeah, both of those things would operate. I don't think it's a two-step process for the retina. I think they were saying that just straight up, it could actually register single photons, which is pretty amazing. Usually even solid state detectors, I mean, the way that they actually get better speed, so to speak, is to have a large enough bin over which to collect photons. So they actually do have to collect multiple photons to make a signal.
Cool, if we had silver and eye, this worked, then we could do that. But I know that with CCDs, they're not silver crystals, so they don't respond to a light hypersensitization. But when you said that human eyes could respond to a single photon, that seems pretty difficult.
Yeah, definitely.
Thank you. Just an aside, if you look at the comparative anatomy of mammals, our ocean-going cousins, the whales, have a greater density of retinal cells, and they can see many more stars than we can, down to much smaller, I mean, larger magnitudes,
Mhm.
right? So a little aside there.
So they have this because they're dark deep waters.
I don't know why it was driven that way. I can't ask why, just look at the way it is.
I
I
guess.
know light extinction through water, it happens pretty rapidly.
Yeah.
So if they go very deep at all, they're going to need a lot more.
On your telescope, when you fall off your tall ladder and you hit the ground with your head, you're going to see a lot of stars.
Yeah.
Hey, Jeff, there's a question from, I think it's from Mike in the chat. Eric, can you see that?
Yeah, I can. The question is basically for newbies, new to the hobby, do you have tips or advice for spotting deep sky objects, as an example, M31? And then also, what are your thoughts on phone apps like Stellarium?
Is that for me?
Yes.
I'm not familiar with Stellarium, but I know that there's lots of excellent planetarium programs for phones these days. I myself use Safari, and I don't know, it's just the one I've been using for years, so I don't know if it's better or worse at all. So I wouldn't necessarily give it a huge recommendation, because I don't know what the competition looks like right now. The other object was, or question was, tips for newbies, and I'd say just go out with the other club members to a star party, and they're going to be right there and more than willing, I'm sure, to help you out. Yeah, just make sure you at least have clothing that will enable you to stay warm, because that's one thing that newbies forget.
Another comment, please? Your question for Joe.
Daniel, our eyes also suffer from a problem called after image.
Yeah.
I mean, if you were to stare at the American flag for a period of time and then look away from it against the white surface, you'll see the same flag, but it will be in opposite colors.
Yes.
Does this affect our observations? If we're looking at something that's colored, do we not get after image influences?
That's an excellent question, but I'm not sure that I can think of. That would probably only be a factor if you're looking at really bright objects. Probably like if you look at Jupiter with a really large telescope, it's like looking at a welding light compared to the other deep sky stuff that we look at. So I could imagine that it could possibly happen there. Essentially, what's going on there is that when you stare at the American flag for a while, the particular cells that are being constantly worked will actually literally get tired. And what will help that is to increase, again, the sugar and oxygen availability to those cells. But literally, because they're tired and kind of worn out from being hit with that stimuli, and the ones that aren't then cause that almost a reverse color image that you see. That's the after image, is usually inverted color. And so, yeah, it's a differential between the cone cells that are stimulated versus the ones that aren't. And then you suddenly look away from that image, you will see that after image.
Telescope. You have a really neat arrangement where when you pack up your telescope, you have like a 3-layer elevator system where it's got your base, then your cell, then your mirror. Do you have any videos of that working that you can YouTube or anything?
I don't have any videos of that because it happens so slowly. It'd have to be a time lapse. But yeah, I have this arrangement that it comes in and kind of cradles the critical components one at a time. And so then I use trailer jacks, start jacking up the corners around the telescope. And then so it'll actually pick up the mirror cell first. So it's kept separate from the rocker box. So it's kept separate from the kind of the ground plate. And then I have them so that they're cinched down so they can't contact one another during transporting. So that's the reason that I did it that way.
Yeah, really appreciate it if you can like maybe sometime make a video of that and get it to us, because we're having mirror hammering issues going into the site that we go into. And I know a couple of people that'd be really interested in seeing that assembly in action.
Yeah, I'll try to remember that and do a video.
Thank you.
Sure.
Yeah, I have a question.
Mhm.
It's Casey Foley. You mentioned, Daniel, that you, if you're looking at an object that you haven't seen for a while or you've never seen before, you want to look at it before looking at any pictures of it. But so your eye has, I forgot what the term was, become accustomed to the dark. You're looking at the object, but then you said, then you look at a photograph of it, and then you look back at the object. So I'm just wondering how you can do that without losing that darkness you've built up in your eye, which I forget what you call.
Yeah, the dark adaptation.
Yes.
Yeah, you're right. You kind of, when you want to look at a photo, then you have to use some of that up, I guess.
So you use regular light, you don't use it in
Well, usually I try to use red light, yes.
red light. So you do use red light, okay. Or not
Mhm.
on your phone, a picture of it on your phone. or-
Yeah, the phone, you can turn on the dark adaptation feature where it just uses red colors, I guess.
Right.
Yeah,
Okay. I was just wondering how to do that. Okay. Thank you.
Yeah. Good question.
Anyone else got it?
Also real quick, talking about the red filter, you can purchase actual red filters to place on top of your phone as opposed to using a software mechanism to do
Yeah.
that. So that's an option.
Yeah, I know that there's several vendors of material like that.
The basic rule of star parties is no cell phones and no computer monitors. And if you do, find something 200 feet away. But even if it's pointing in the other direction and it's lighting up the ground behind you, it's very difficult to truly dark adapt at a dark sky star party.
Yeah. That might be one reason why visual observing is kind of falling off in popularity. People don't want to be away from their devices.
Well, Dan, thank you very much. It's been exciting seeing you again.
Yes, you too.
And we will continue this at some future time because you're a lot of fun. So thank you very much, Dan. And here's some applause for you.
Thank you, everyone.
We are going to segue onto our regular meeting. You're more than welcome to hang out and pay attention to this very boring section here, but we appreciate you coming and talking to us and showing us the northern lights behind you there.
Yeah.
All right, ladies and gentlemen, we are going to move into the business part. We're going to try to do this as quick as possible. I think I will start if you're ready for Tim. Move on to the calendar of events and activities, which will be known now as the Tim and Doug Show.
Okay, Eric, are you gonna share your screen or you want me to?
Take it away, Tim.
If you want to show, you can.
I'll find it here. Yes, I just put together a slide here with upcoming events coming up in the sky and on the ground for September and October. So y'all can see the screen now, can't you?
Yep, we got it.
Okay. So starting off September 17th through the 30th, the zodiacal lights are going to be visible. I've never actually seen them, so I'm looking forward to kind of taking a peek and giving it a try this year. And hopefully we can get some dark skies and be able to see that kind of cool phenomena. September 17th is our Highway 4 Star Party. Always a good time out there. The weather should be nice and cool by then. The 23rd is the autumnal equinox at 6:03 p.m. And then on September 24th is our high altitude star party and yearly potluck at Peddler Hill. So hopefully you all can come out, even if it's just for a few hours that evening. Should be really nice weather and some good viewing. And if Peddler Hill is not accessible for whatever reason, we'll go to our backup spot at the heliport. So keep in touch with the members of the club and our Yahoo chat board for updates on that as to where we're going to be and what the conditions are like. And then we're going to be very close on the 24th to the September 26th opposition of Jupiter. So hopefully we're going to get some nice bright views of Jupiter while we're up there. And then as it is at opposition and its brightest on the 26th. Into October, Doug's got a few star parties. Doug, let me let you go ahead and announce these.
All right, well, October 1 was their first astronomy in the park for the month. October 4, we've got a star party for a kind of a special school. It's the Challenges Discovery Challenge Academy. If you would like to participate, let me know. Assuming that Eric and Bill and Frank are available. We pretty much have this one covered. We've been doing this one for many years. But if you want to join us, like I said, let me know because I've got to get your information and give it to them at the gate. And then October 29, we will do another astronomy in the park because October has 2 Saturdays with close to the first quarter moon. November, we will not have a astronomy in the park. Actually, there's one more event that's kind of half baked and it might come to fruition is on October 14. Sandy Adams, the lady that allows us to use the nature center here and helps us out so often, is trying to put together what she calls a trunk or treat at Mickey Grove. And thinks she'd like to have us have some telescopes out there and possibly giving away candy and so forth. So I'll get more information on that and I'll send out an email for volunteers on that one if it actually does come together. And back to you, Tim.
Okay, October 13th is our next general SAS meeting. And I think Jeff's got another great program in store for us. I don't know, Jeff, if you want to do a spoiler alert or just keep us waiting to see what
we had a request to do some basic astronomy, so we're going to have a fall skies workshop and a basic astronomy discussion with it, and we'll pull this from members of the club.
Very good. October 15th is our Highway 4 Star Party again, and then the high altitude on October 20th. Again, hopefully our weather is really nice then, and we're free of wildfire smoke by then. And then the 21st and 22nd is the Oronid meteor shower peak. So try to get out for that and see some showers of meteors. And that's pretty much it that we've got planned for September and October. This slide here, I'll let you take it over, Jeff, and talk about this announcement.
Looking at the telescope and going, what?
Yeah.
Okay, I guess I should read. Yeah, we have a lot of storage issues. Jerry's got an awful lot of stuff over at UOP. And we're going to be losing that area because he doesn't work at UOP anymore. And we're looking at an issue of storing, how many square feet of floor space storage do you think we need, Jerry? We need about 100 square feet to store some telescopes, some records, some Custer slides, materials. So there's optical stuff and there's non-optical stuff. We need about 100 square feet. And it'd be really nice if we didn't have to rent a storage somewhere. So if anybody out there in SAS land has an idea or an available spot, let the executive committee know as quickly as you can, because it is not going to my garage. And we can always put it in Jerry's backyard. He's got a really nice backyard with a view of a lake, you know, can all go back there. So please, if somebody out there has the ability to store some of our stuff, very cool. I appreciate it. Tim, are you all done with your stuff?
I am, Jeff, but before we leave this slide, I want to see if anybody knows what telescope this is.
Say that would be the hooker.
It's the hooker. Yep. This is the 100-inch hooker telescope that was at Mount Wilson, that was used by. That's right. To detect the Cepheid variable in Andromeda. So historic scope, if you're ever in Los Angeles, try to get down there. They do tours of Mount Wilson, and you can get into the observatory and see the historic Hooker telescope.
Yeah, when you're down there looking at it, you'll see there's a tail rat on it, which is really hilarious. All right, thank you, Tim and Doug. We are going to move on to the business part here. The executive committee is recommending that we vote on something tonight. It was in the newsletter, so it's an official thing to vote on. And so here it is. In August, the SAS held its first in-person meeting since the COVID-19 shutdown. We've chosen the Nature Center at Oak Grove Park as our initial meeting site. The Nature Center lacks a reliable high-speed internet connection for the Zoom portion of our meetings. Club secretary and superb high-tech professional Eric Holland has taken it upon himself to purchase much of the equipment and the internet subscriptions necessary to hold these meetings. We don't know yet what our final equipment setup will be. That is an ongoing experiment. We do know that we will need to keep using the high-speed internet connection Eric has set up for us. This is an item that is outside of our budget for the year, so we are asking the club to make a motion to vote for permission to pay Eric Holland $50 a month for the final 5 months of the year, August through December, for a total of $250. And that will get us through the year. And then in January, when we make our next year's budget, we would be able to put that expense into the budget and have the membership vote the budget, and then it would be a moot point. But for at this moment, we are recommending to the club membership that somebody makes a motion to pay Eric $250 for this final 5 months of use. Okay, Don Lucio has moved. Do I hear a second? I heard Doug Christensen make a second. Any discussion on this topic? Do I have a motion call for vote? I heard the motion. All those in favor say aye. And anybody opposed, please say nay. The ayes have it. It has been moved, seconded and voted on. And so Eric, you're going to get $250 here. Thank you, SES membership. Okay, on to the announcements part. Frank Drake, who came up with the formula for probability of other life in our galaxy, has passed away. He lived over here in the Bay Area, and I tried to get him to come over here a couple of years ago, and he was too old and tired and didn't want to do it. And I guess he really was kind of old and tired here, but he did pass away. I think, was it day before yesterday? Oh, it died on Friday. Okay, thanks, Doug. All righty, another one that Eric wanted me to bring up is that you can find the SAS meeting recordings on a link at our SAS page at stocktonnastral.org. So that is now available for you to see recordings of our meetings. All righty, well, there was one last thing, and that is the Starbucks card giveaway. I have one, and it's going to go to somebody who is actually here in the room. So, Dan Bakken, are you still with us? Okay, so let's go with Bob.
Hello?
How you doing, Bob? Could you pick a number between 1 and 10? Make it a natural number between 1 and 10.
7.
Number 7 is Jerry Hunt. Congratulations, Jerry. Thank you, Bob. Thank you, Jerry.
Not a problem.
There we go. Okay, so that ends our meeting, except for we have cookies here and you don't. So, yeah, you can watch us eat the cookies, but we can stay connected as long as you want. Our official meeting, do I have a motion to end the meeting? Yeah, okay, all in favor say, yeah, quit. All right. All right, thank you, everybody, for showing up both live and on Zoom. And we'll see you again at the October meeting. Bye-bye.